Hello, everyone, and welcome to another wonderful day of physical chemistry. So, today we're going to be finally focusing in on how we can turn probability densities into probabilities. So, a good place to start is the fact that we know that we can get a probability that the probability of finding a particle is going to be proportional to the probability density, of course, times um, the distance in the x direction uh, described by said probability density, which of course really ends up showing us that the probability is going to be proportional to an integral over our probability density. But at this point, we now need to take a step back and try and ask ourselves, what's the likelihood of finding a particle anywhere in space? So if we integrate our system over all space, well, it turns out the particle has to be somewhere. So if the particle has to be somewhere, the total probability has to be 1. But this means we also have to integrate our system over indeed all space. So from negative infinity to infinity. This can again be modified in systems where we've already constrained our particle to be within some given subrange of negative to positive infinity. But in the general case, we want to go ahead and integrate our system from negative to positive infinity. Now, we run into a slight problem that many wave functions actually kind of fail to satisfy this expression. So what we can do is try and modify each of our wave functions by multiplying the wave function by a value of n. Now, this n is going to be called the normalization factor or constant, and it shouldn't have any dependence upon position. And as such, these two n's, one from each wave function, should be able to be pulled out front as an n squared. So even if this isn't true, I can definitely choose an n such that this is true. So no matter what my wave function is, I can just normalize it. And normalizing is a way of talking about making sure that the integral sums to 1. So this normalization constant actually does have a fairly easy equation for its solution. Well, all we need to do is say, uh, move our integral over to the other side of the equation, so divide it, and then take the square root of both sides. And because the square root of 1 is 1, then what we get is n over the square root of our integral over all space. And occasionally this is presented as just putting our exponent as negative 1/2 to illustrate that this expression is in the denominator. So once we've done this, what we need to try, uh, we're going to need to try and find, this will allow us to construct a normalized wave function. So again, a normalized wave function is simply one way of saying of which we have a wave function for which this is true. And in general, we're going to treat many of our wave functions as being pre-normal, as being normalized. And as we move on, this will often be taken for granted. But occasionally, in order to determine the true structure of a wave function, we need to find a way to normalize a wave function ourselves. However, one of the things I do want to make note of is that all wave functions aren't going to simply be one-dimensional. We also have three-dimensional wave functions, at which point we need to make sure that when we take the integral with respect to x, y, and z of my probability density, that in sum still gives us a probability of 1. So indeed, my particle is located somewhere in this three-dimensional space. However, because working with multivariate systems is often complex, we often just reduce this form to a general variable of tau, where tau is going to represent overall space. So it's a way of saying I may have a 3D system, but it doesn't matter whether it's an XYZ or R psi phi. No matter what, as long as I take the integral over all space, it still needs to equal 1. And again, we're going to generally assume that most of our wave functions are normalized. But we have to give ourselves some practice first. So let's go ahead and start with a simple wave function. So let's say that I have a particle with a wave function of essentially sine pi x over L that I know exists somewhere between 0 and L. Well, I want to try and find out what is my normalization constant for this wave function. So again, just for some background, sine pi x over L should give me a wave function that looks like this going from 0 to L. So I know that my particle is constrained somewhere in this distance L. So what we're going to want to do is start with normalizing our resulting equation. So we're going to integrate from 0 to L because this is all space for this wave function. Then I'm going to take the square of this wave function. Here I get very lucky. I don't have to worry about complex conjugates. There is no I. So it's just simply the square of the wave function. I can then pull n squared out front, and then I have to integrate over sine squared pi x over L. Now, this is actually a tricky integral, but it turns out that this is one with a known analytical solution. So you can go ahead and look up in your integral table in your equation sheet, or use any of the integral tables in the back of your book or online, and you'll find out that we can essentially truncate it as this equational form based on our value of L. So this kind of gives us a little bit of a fun equation, but it is worth noting that here we have 2 pi L over L, which just truncates down to 2 pi. However, sine 2 pi, well, sine of any integer of pi is going to give me a value of 0. So it turns out that we get very lucky in this circumstance in that this expression goes to 0. So all we're left with is n squared over L times L over 2 equals 1. So we can then go ahead and rearrange this and find that our normalization constant is going to be square root of 2 over L. So what this ends up meaning is that my normalized wave function is simply going to be inserting this normalization factor into the general wave function, which gives me a wave function of square root of 2 over L times sine of pi x over L. And it turns out that this is actually the exact equational form that I have graphed here, where what is really important about these general expressions is that the sine pi x over L is really giving me the shape. What this normalization constant really gives us is the height. So it figures out how much I have to scale this wave function up or down such that the area under this shape sums to 1. However, one of the useful things of once we have a normalized wave function, we can use this wave function to determine the probability of finding a particle in a given area. So let's say I want to figure out what's the probability of finding this particle in essentially the central half of this system. So somewhere in between L over 4 and 3L over 4. So the 1/4 to the 3/4 mark. So doing this, what we can do is set up the same general expression, now with my normalized wave function, and just change the bounds of my integral. Now, this gives us a little bit of a complicated integral, but again, making use of your integral tables, you can reduce the system to 2 over L because that comes out forward. And then we have essentially this x over half and then minus this fun sign-dependent term. But here's the problem, is that this is going to be the general definite solution. And we still need to figure out what the solution is under the bounds of L over 4 and 3L over 4. So we can then apply these bounds. So we put in 3L over 4, and then we essentially subtract out the same expression with L over 4. This gives us, well, let's be honest, a fun little bit of algebra. A good way to try and solve the system is first by trying to collapse down our sign expressions. So here we have sine over 3 pi over halves, which is going to be -1, and sine of pi halves, which is 1. So that gives us essentially a little bit more of a simplified form. My negative turns positive, and here, because I have a minus of a minus, this sign turns positive as well. So then we can try and first sum to get first factor out our 2 over L, which gets rid of all of our L's and simplifies all of our denominators. And then we can combine all the factors that don't have pi and then all the factors that do. And when we do this, the whole system sums to 1/2 plus 1 over pi. So this gives me a probability of 0.82. So this is the same as saying we have an 82% probability of finding the particle in the middle of the box. Now this kind of may seem a little bit weird because it's half of the area, but then we have to realize that this is the half of the area where everybody tends to be located. And so being able to make use of these normalized wave functions is going to be absolutely fundamental in determining the probability. And as you can imagine, as we start applying this to things like particles being trapped in a box or around an atom, knowing exactly where that electron is going to be, or that proton or that neutron, is really going to change the dynamics and the behavior of the system. So we'll go ahead and make a little bit more use of these probabilities next time. Till then, take care.